exam was 52%. Okay, the scores are, of course, on Blackboard. You can kind of see the distribution. It's a bimodal distribution. If you look at the number of scores as a as a function of the score, you make a graph of it. It has two bumps. One bump kind of in the 80s and 90s in terms of percentages, and another bump sort of in the 40s, 50s, 60s, with a kind of little valley in between in the 70s. So anyway, since the average is fairly low, I will grade 5 points easier than what the grading scale on the syllabus in terms of how the number grades translate to letter grades. So for example, on the syllabus, I think it said 90 to 100% was an A. So I'll do
85.
Does it say 85? Okay, so I'll do 5 points lower than that. I'll do 80 to 100 then. So in other words, all the boundaries between the grades move down by 5 points compared by what's in the syllabus. Okay. So the solutions to the midterm are available online, and I certainly encourage you to look through those, especially on any question that you got wrong, and see how it was supposed to have been done. I did try to make comments on your paper wherever there was a mistake, but obviously there isn't enough room to write kind of everything. So definitely take a look at the solutions, right? That is a good way of studying for the final exam. Now, speaking of the, maybe I shouldn't say speaking of, because it's not the final exam. I want to talk a little bit about the second midterm. And I want to throw out an idea for you to think about, and if you want to, we can decide this on Wednesday, but I want you to think about it at least between now and then. I know I promised you 2 midterm exams, but we're pretty late in the quarter, and we're kind of behind schedule compared to where I would like to be at this point in terms of the material we're covering. So I'd like to propose the idea of not having a second midterm. You can turn that in Wednesday if you want. So, wait, Nam, I've got your test. So I'd like to throw out the idea of not having a second midterm. Okay? I'm not going to do this unless you agree, because I know I promised you one. Okay? But if you agree not to have one, here is what I would propose. In terms of grading, okay, the percentage of your grade, and you've got a syllabus here, I've forgotten exactly what it is, but whatever percentage I said would be based on the second midterm exam, namely 25% of your total grade. What I'd be willing to do with that, if we don't have the second midterm, is to use either your first midterm grade or your final exam grade, whichever one is higher, okay, as your second midterm grade. So that would give you, a little bit of an advantage in the sense that you would have 2 shots, and again, whichever one is better. Obviously, if you did well in the first midterm, you're probably not disappointed about using that grade twice. If you didn't do so well, but you think you have a good shot at doing better on the final, then that grade would count twice. So that's how we would do it in terms of grading. So I want you to think about whether that's something you'd be willing to go along with or not. And I don't know, I guess if you feel ready to vote on it now, we could do it. If not, think about it and we could vote on Wednesday. Maybe we should vote on when to vote first. Do you want to vote now on whether to do this, or do you want to think about it till Wednesday?
If we had a second midterm, would we drop that if we did bad on it, or is there any options if we have the second?
I don't want to take a day to do a midterm if that score isn't going to count for anything in the end, because we're already way behind schedule. If we have a second midterm, that means we lose a day of lecture in class, and we can cover even less material than we would otherwise. So unless that test is going to count, I'm not willing to lose the day and do it. Okay, so no, I'm not willing to consider dropping it. Okay, so your choices are either we have the second midterm as promised in the syllabus. I'm not sure exactly what date it would be at this point, but obviously it would have to be soon because we're getting near the end of the quarter. If we don't have it, I would, again, take either your first midterm grade or your final exam grade, whichever is higher. So for some of you, that would be the first midterm. For some of you, that would be the final. And just count that, double count that as your second midterm grade as well. Okay? By the way, I'm also, just in case the grading issue is a big factor in your thinking about this and your decision. Let me point out, I am probably also, the last homework assignment of the quarter, I think, will be an extra credit homework assignment. So you will have a chance via that to also improve your grade. Okay? So do you want to decide now on the second midterm? Or you want to wait and think about it on Wednesday? Yeah?
If we got the second midterm, could we still get some practice tests for it?
Sure, I'd still be willing to post a practice test for it because that would give you,
More study material
for the final. Sure.
And the second midterm would just be Laplace?
It would be Fourier series and Fourier transforms. We'll get to the issue of Laplace in a minute. There's a second question we have to consider. And actually, maybe I should throw this out because it might be related in your thinking to the first question. So continue to think about the question of the second midterm. Here's the other question I want you to think about. Originally, we said we were going to cover 3 topics. The first is vector calculus, which of course we finished at this point. The second is Fourier series and Fourier transforms, which obviously we're doing right now. The third one is ordinary differential equations. I'm thinking at this point, especially if we have a second midterm, because we would again lose a day of class to that, I don't think we're going to have time to get through all of ordinary differential equations. So we've got 2 choices. We could either start on it and get maybe halfway through it, and then finish up the second half in 473 in the fall, for those of you who are planning on continuing with that. Or we could skip the ordinary differential equations for now, do it first thing in the fall in 473, and instead, for the remainder of this quarter, after we finish Fourier series and Fourier transforms, we could talk about Laplace transforms, which are actually closely related to Fourier transforms, which in turn are sort of related to Fourier series. We could talk about a little bit about differential equations because actually the method of using Laplace transforms is a way of solving some differential equations, and we could talk about that and enough about differential equations for you to understand kind of what we're doing with that method. And then also talk about things called convolutions, which are related to both Fourier transforms and Laplace transforms, and something called the Dirac delta function, which is a very useful thing to know also. So if we did that instead of ordinary differential equations, I think we would have time to get through that in the remaining time we have. Those are all fairly short topics. And for those of you who are computer engineering majors, I think Laplace transforms is actually, that would be really useful for the computer engineering majors. The ordinary differential equations are useful too, don't get me wrong, but you know, if anything, I think the Laplace transform stuff might be even more useful for the computer engineering majors. One thing in my thinking about this is whether to go ahead and do this change or not, is I'm wondering for the physics majors in here, not the computer engineering majors, but the physics majors, I would feel bad about you not seeing the ordinary differential equations if you're not going to see it elsewhere. In other words, if you're not planning on taking 473 in the fall, or maybe the next year. I mean, you could put it off a year, obviously. But if you're not planning on taking 473 at some point, then I would feel that maybe we should do the ordinary differential equations now, because I really think you need to see that material. So one of the questions in my thinking is, first of all, how many of you are physics majors? Oh, more than I thought. Are all you physics majors planning on taking 473? Is there anybody who's not?
I'm not going to take it next quarter, but I'm
Not
going to
next
take
quarter.
it next year.
Okay, but you will take it at some point.
Yeah.
Okay, is there anybody who's not going to take it at all? Okay, because the problem there then is if we don't do ordinary differential equations this quarter, then you're not going to see it at all. And I don't think you're going to have time to get through the whole thing, even if we do it this quarter. So this is a problem also. So I'm really torn at this point. I'm honestly not sure what the best thing to do is.
I think a good alternative is to just not do the second midterm then and spend more time doing ODEs.
Okay, but even if we do that, I don't think we'll have time to finish them.
Okay.
So they take about two to 2.5 weeks to do.
Okay. Then we'd have to start them today.
We'd have to start them today, yeah.
And we're not even.
And we're not done with Fourier series yet. So.
Would a take-home midterm be an option? since we're on a time crunch?
You know, I used to do all the exams as take home in here. And to be honest, you know why I don't do them that way anymore? It's because too many people have access to the solutions manual online. And every problem I can think of, you know, you're going to be able to find it
There's a
somewhere
close exam
online.
out there, yeah.
And so the last time I did take home exams, I found that so many people were copying the solutions from somewhere online instead of doing the problems themselves, that I just decided it was not doable that way anymore. So that's the reason we're doing in-class tests. So no, that would be the problem. That's why I'm not willing to do that either. Anybody else have any further thoughts on this question? By the way, a few people have come in late. You could raise your hand and I'll give you back your midterm if you came in late. What's your name? Corey. Corey Cook.
I got like 40-something raw score.
Okay, so we've got two decisions basically. We've got the decision of whether or not to do the second midterm, and we've got the decision of what topics to do for the remainder of the quarter once we finish the Fourier series and Fourier transforms. Do you feel ready to make a choice about the second midterm right now?
I think I'm ready, yeah.
Or do you want to think about it, talk about it on Wednesday instead?
I'd rather do that.
Okay, let's vote on when to do the vote. Okay, how many people want to decide right now?
Majority rule.
How many people want to wait and decide on Wednesday?
Those are the people who probably don't
Okay,
have the
that's,
midterm.
sorry, folks. Okay, so about the second midterm then. So raise your hand if you're willing to skip the second midterm and use either your first midterm or your final exam grade, whichever is higher, in place of your second midterm grade. So I'm going to count this time because I want to make sure I get it right. So leave your hands up.
Oh, I didn't do that well. I just
Don't want to take another test.
no. It just seems the appropriate thing to do.
Okay, how many people want to have a second midterm as originally promised in the syllabus?
Like raw score 40s.
Okay.
People that start raising their hands.
Okay, so it looks like, and it looks like some of you didn't vote, which means you probably don't really care one way or the other. But of the people who voted, clearly the majority said to skip the second midterm, so we will do that. So then the second question is, once we finish the Fourier series and Fourier transforms, whether we're going to spend some time doing Laplace transforms, their applications to differential equations, and some related things like convolutions and direct delta functions, or whether we want to start as originally planned on ordinary differential equations. Whichever topic we don't do this quarter, we will do in 473 in the fall. Okay, so I mean, we'll cover both topics eventually for those of you who take both classes. Okay, but for those of you who don't, again, you know, it's a question of what you're going to miss this way. So again, for the computer engineering majors, I think it's probably better for you to see the Laplace transforms this quarter. For the physics majors, if you're going to be in 473, it doesn't much matter. But if you're not going to take 473, then it would be better for you to see ordinary differential equations this quarter, I think. Especially if you're not an applied physics major. If you're an applied physics major, there's maybe an argument that's the same argument I gave for the computer engineers, that maybe the Laplace transforms might be better for you also. Although it's probably approximately equal. Do you want to decide on that today? Or do you want to decide on that on Wednesday?
To decide today.
Sure.
I'm ready.
Okay. Okay, if you'd rather do the ordinary differential equations as originally planned, raise your hand.
Oh, wait.
Seems she's
Well, how many did we have that won't be taking 473?
Looked like there were 3 or maybe 3 people or so.
I need to know if I'll feel bad if I vote the other way.
Don't take 473 this fall. Would you still teach it the same way?
Well, I guess it depends on whether I'm teaching it. If you take it, if you do take 473 this next fall, I am teaching it this next fall, and so I know what I cover, what we're covering this spring, and I will adjust what I cover next fall accordingly. If you take it in a future year, I suppose it depends on who teaches it, because it might not necessarily be me. Now, if it is somebody else, I will tell them what I did this year and ask them, to kind of rearrange what they're covering accordingly. But I can't promise for sure that they would do that, especially if it's only 1 or 2 people who missed some material. They may say, oh, make it up on your own or whatever. So again, you'd be in for a little bit of uncertainty if you're in that category, since I don't know for sure. Okay, so we're ready to vote. We actually took the first, I forgot the number though. So if you'd rather stick with ODEs, ordinary differential equations, as originally planned, raise your hand. If you'd rather do the Laplace transforms and related stuff, raise your hand. Okay, that's clearly a majority. Okay, so we will do the Laplace transforms and convolutions and so forth then. I will say a little bit about ordinary differential equations because, as I mentioned, Laplace transforms provide a technique for solving some differential equations, and that's one of the things I want to talk about in connection with Laplace transform. So we will touch on ordinary differential equations briefly, okay? And for those of you who are not planning on taking 473, I will be happy to give you a copy of my notes on the differential equations material so that if you do somehow miss out on it, right? If you don't take 473 or if you take it a year from now and it's taught by somebody else who doesn't cover that material, then you'll at least have my notes, and between that and the book, hopefully you can study that material on your own and learn it, because it is important material that you should know. Okay? Okay, and again, Daniel and anybody else there, I know there are several people in here who have to leave early before the end of the quarter to go to REUs for the summer or summer research programs. And for those people, they wanted to know what we were doing so you could start studying ahead. And I'm sorry I didn't let you know before now, but I wanted to decide what topics we were going to cover, because that would affect, obviously, what notes I gave you and so forth. So anybody in that category, like Daniel, I know there are a couple others too, talk to me. I'll be happy to give you my notes on the material we're covering for the end of the quarter, so you can kind of study ahead if you're going to take the final early. Yeah?
You said you were going to make the last homework assignment extra credit?
Yeah.
For those that are going to be gone, do we just do it and send it to you when we're gone?
Yeah, you can do that.
Okay.
If you want to turn it in before you leave, that's fine, of course. But if you want to do it while you're on and email it to me, that's fine too. Okay, so anyway, last time we were doing an example of a Fourier series, and the example was a square wave, and we didn't quite finish it, so anyway, our function, if we draw a graph of f of x as a function of x, our function looked like this. Right, so it's a square wave. The value at the top is 1. The value at the bottom is -1 along the vertical axis. And along the horizontal axis, let's say there's pi, there's minus pi, this is pi over 2, 3 pi over 2, 2 pi, and so forth. Okay? So in other words, this is a function that has a period of 2 pi. And remember, we were using the notation capital L for the period, so that would be the value of capital L. Right? And let's think of the range from minus pi to pi. we define the function f of x over that range, it is equal to plus 1 for values of x between minus pi over 2 and plus pi over 2. It's equal to minus 1 for values of x between minus pi and minus pi over 2. And for values of x between pi over 2 and pi. Right, so again, that defines the range from here to here. Right? And then, of course, the function just repeats that same pattern for larger and smaller values of x. So anyway, we said that in general, a Fourier series f of x, this is the general expression, not just for this example. F of x is equal to a naught over 2 plus a summation from n equals 1 to infinity of a sub n times the cosine of 2 pi nx over L plus b sub n times the sine of 2 pi nx over L. And of course, in our case, with L equal to 2 pi, we just have the cosine and the sine of nx, right, as the argument. And we have formulas for finding these coefficients, the a sub n's and the b sub n's. A naught, let's actually write the general formula first. So a naught was equal to 2 over L times the integral of f of x dx. And our limits of integration are from x naught to x naught plus L. Right? And x naught really can be any number. Although we usually use x naught equal to either 0 or to minus L over 2. Okay? And a sub n is 2 over L times the same integral. Sorry, not an equal sign there. 2 over n times the same integral from x naught to x naught plus L of f of x. And now in the integrand we have a cosine of 2 pi nx over L dx, and the b sub n's, the coefficients of the sine terms, are the same integral except with a sine instead of a cosine in it. Okay, so for our example, we found that a naught was equal to 0, and a sub n, by the way, notice this formula will work for a naught also, because if you put n equals 0, you have the cosine of 0, which is 1, so it looks just like this integral right here. And we found last time, this is the very last thing we did before the end of class, we found that a naught was equal to 0, or a sub n, I'm sorry, was equal to 0 for even values of n. And it was equal to 4 over n pi for every other odd value. So 1, 5, 9, etc. And it was equal to minus 4 over n pi for the other odd values of n. So 3, 7, 11, and so on. Okay? And we haven't yet found the b sub n's. Okay? So for the b sub n's, again, our period L is equal to 2 pi, so the 2 over L becomes a 1 over pi. In the integral, and I believe we did the same thing for the limits, oops, this is an x naught down here. For the a sub n's also, we used x not equal to minus pi. So in other words, our limits of integration went from minus pi to plus pi. Right? We're always integrating over one period. And, you know, probably the most convenient limits to use in most cases would be x naught equals minus L over 2. Then, of course, x naught plus L. The upper limit is plus L over 2. Right? So in other words, we have symmetric limits of integration. The lower limit is the negative of what the upper limit is. And we'll see why that's a convenient choice to make in just a minute. Okay, so anyway, we've got an f of x times the sine. And again, when L is equal to 2 pi, the argument of the sine is just nx dx. Okay? Okay, so if we split this up depending on f of x, right, it has these different values over these different ranges. So we should split it up into 3 terms, one from minus pi to minus pi over 2, one from minus pi over 2 to plus pi over 2, and one from plus pi over 2 to pi. And so f of x is equal to minus 1 for that first range, so I'll pull the minus sign out in front. We've got a sine nx dx then in the integral. The limits run from minus pi to minus pi over 2. And then from minus pi over 2 to pi over 2, over that range of x, f of x is plus 1. So we just have the integral of sine nx dx. And then from pi over 2 to pi, f of x is minus 1, so I pulled that minus 1 out in front. All right, so all the integrals are the same. We've just got different limits on them. The integral of sine x is, of course, minus cosine x. Right, so we've got 1 over pi times cosine nx divided by n, right? We have to evaluate it at the limits. Right, the integral of sine gives us minus cosine, so for the first integral, that minus sign cancels with the minus sign in front. For the second integral, the minus sign stays there. And then for the third integral, we get a plus sign. Okay, so out in front, I'm going to pull out a 1 over n, since that appears in every term. So we've got a 1 over n pi out in front. And so then we have, if we evaluate the cosines at the limits, from the upper limit of this one, we have a cosine of minus n pi over 2 minus a cosine of minus n pi. And then from the second integral, this one right here, since there's a minus sign in front, we have a minus cosine n pi over 2 from the upper limit, and a plus cosine of minus n pi over 2 from the lower limit. And from the third integral, we have a cosine of n pi from the upper limit, minus a cosine of n pi over 2 from the lower limit. Okay, so remember that cosine is an even function? And remember what that means? It means the cosine of minus x is equal to the cosine of plus x. So that means that, for example, the cosine minus n pi here is the same as the cosine plus n pi, but that one's got a minus sign out in front. This one has a plus sign out in front. So those two terms, for example, will cancel. Okay? Turns out all these terms will cancel. I'm just going to use the arrows to match up and show you which ones cancel with which. Right? Cosine minus n pi over 2 is the same thing as cosine plus n pi over 2. So that term cancels with this one. And let's see, what's left? Again, cosine minus n pi over 2 is the same as cosine plus n pi over 2. So that one here cancels with this one there. So all of our terms cancel. And so b sub n is equal to 0 for all values of n. There's actually a shorthand way we could have realized that, okay, that I will come back to in a minute. But before we talk about that general situation, I want to just sort of finish up this example first. So our final answer for the Fourier series, right? All I'm doing at this point is I'm writing this equation right here. And I'm going to plug in what the a sub n's and b sub n's are. The b sub n's are, of course, 0, so those terms are all gone. A naught is 0, so that term is gone. So we've only got these terms right here. And again, some of the n's, the even n's will be 0. So let me just write out the first few terms. I'm not going to do it in summation notation. I'll just write it out explicitly, since the a sub n's are, it's different for different values of n, basically. So n equals 1 will be the first non-zero term. When n equals 1, the coefficient, the a1, is 4 pi. So we've got 4 pi times the cosine of x. Remember, again, with L equals 2 pi, we just have the cosine of nx, and of course n equals 1 for this first term. The next non-zero term is for n equals 3. In that case, a sub n is minus 4 over 3 pi. Right? So minus 4 over 3 pi times the cosine of 3x, right? It's nx, so n is 3 in this term. The next one with n equals 5, that's the next non-zero term. The a sub n, or a5, will be 4 over 5 pi, and that will multiply the cosine of 5x. Then we'll have a minus 4 over 7 pi times the cosine of 7x plus 4 over 9 pi times the cosine of 9x, and so on. Okay? Now, just before we leave this example, because I think this is a good example to try to give you an intuitive feeling for what these terms in the Fourier series are actually doing. So I actually want to make a graph. And on our graph, this is, normally I prefer to teach in rooms with blackboards, not whiteboards. I really hate whiteboards, but this is the one time I like a whiteboard, is to do this one graph that we're going to do because
So different colors?
different colors, yeah. I suppose on a blackboard you could have different colors of chalk, but they're not as readily available. So anyway, here's what I want to do. I'm going to make this really big. So as a function of x, I'm going to make several graphs here, okay? And so let me find my different colors here, and hopefully enough of them will be
Working.
So here's what I'm going to do. I'm going to draw with just blue marker what the first term in the Fourier series looks like. Right? So and for each value of n, right, we've got 1, 3, 5, 7, right? Only the odd terms up here because remember that the a sub n's are 0 for even values of n. For each of these terms, in this little table here, let's put the amplitude of that term, in other words, the term out in front, right? So the n equals 1 term, the amplitude that multiplies the cosine x is 4 pi. For the n equals 3 term, it's 4 over 3 pi, so in other words, it's 1/3 of the amplitude of the first term. The next one is 4 over 5 pi, 4 over 7 pi, and so on. And every other term has a minus sign out in front. Notice I didn't include those minus signs as part of the amplitude. But, of course, that minus sign in those is going to flip those terms upside down on the graph from what they would have without the minus sign. Okay, and so that's going to help us kind of draw this. So, for example, for the first term basically looks like cosine x with a 4 over pi, which is a little bit more than 1, right, out in front. So it's basically going to look like this, right? It starts I'm going to draw that much of it, okay? And now what I'm going to do with another color, I'll use the red, if this is working. As a red dashed line, I'll draw the second term alone, and then as a red solid line, I'll draw in the sum of the first term and the second term added together, okay? So the second term alone has a cosine of 3x. That means the period is 1/3 of what it was for the first one. And of course, by the way, I could label some values on the axis here, right? Like this is, for example, pi right here, minus pi right here. So we have 1/3 the period for the second term that we had for the first term. And since there was a minus sign in front of it, that flips it upside down. So in other words, it starts at its minimum, not its maximum, at x equals 0. And it's got about 1/3 the amplitude of the first term that I've drawn in. So it's going to look something like that, right? I have 3 sort of bumps in it in the same range of x that I had kind of 1 bump for the first term. Right, something like that. Now, if I add the first term and the second term together, notice that they both cross 0 here. They both cross the horizontal axis at the same point, so the sum will cross there at the same point also. I'll just start drawing there. The sum will rise more quickly than either of these did individually because I'm adding functions that are increasing for both of these. There'll be a little bit of a peak right up here where the maximum of this curve is. And then since I'm adding in a negative contribution from the red one, there'll be a little bit of a dip here. And then a peak again, corresponding to the peak here. And it's going to come down, and it's going to sort of repeat that same kind of behavior over here, except flipped upside down. And same thing over here. Okay? So that's what the sum of the first 2 terms looks like. Now let's see what the third term does when we add that in. And I'll use a purple marker for that one. Again, I'll use a dashed line for the third term alone and a solid purple line for the sum of the first plus second plus third terms. Okay, so the third term, that's the n equals 5 term, has an amplitude of 1/5 of the first term, and it has a period that is 1/5 of what the first one was. So I'm going to have 5 bumps, and where I had 1 bump for the first one. And it's right side up, right? It has a plus sign in front of it. So it has its maximum, not its minimum, right, at x equals 0. So it's going to look something like this. Yeah, I'm missing something. No, I'm not missing one. I'm just not drawing it very well. I'm not going to try to go beyond the third term. My artistic ability isn't good enough. Okay? And similarly here, okay? So if we add that term in, that's going to put, again, if we start drawing right here, adding in a function which is increasing is going to make this even rise a little bit more steeply than what we had for some of the first two terms. And it's going to put some more bumps across the top. For example, at x equals 0 here, if I think about the sum of the first two terms already, that's the red curve, and I add in now this purple dashed one, that's going to put a little peak up at the top. Going to produce something that looks sort of like that, and down here sort of like this. Okay. Again, I'm not going to try to draw any more terms because my artistic ability isn't really up to it. But I hope you can see what's happening here, and that's that as we add more terms, it's starting to look more and more like a square wave because the sides are getting steeper. By the sides, I mean this part right here. Okay. We're getting more bumps across the top right there or across the bottom right there, but those bumps are getting smaller in amplitude. So both of those things are going to make it look more like a square wave. It's starting to look more flat across the top and the bottom, and the sides are getting more vertical. Okay? So after many terms, and I think your book has a better graph of this than what I can draw on the board because there's this computer generated, of course, not just drawn by hand. But if we add in very many terms, what we're going to get is something where the sides almost look vertical. We get a bunch of small amplitude but large number of bumps going across the top and across the bottom. And we get a function that is starting to look a lot like a square wave. Okay? One curious thing is that as the number of terms you include goes to infinity, this is of course an infinite sum, right? I've just written the first few terms here. As the number of terms goes to infinity, in that limit, the sides get completely vertical and the tops and bottoms get flat. However, there's a little spike right here at the corners. I'm exaggerating how big it is right here just to show you what I mean. There are spikes like this that appear at the edges that actually don't go away in the limit as n goes to infinity, as the number of terms goes to infinity. The width of those spikes goes to 0, but their height remains at, I think it's about 11% of the total difference between the top and the bottom. That's something called the Gibbs Phenomenon. And those don't go away, but since their width shrinks to 0, they're effectively not there anymore. Now, for those of you who are applied physics majors or maybe computer engineering majors and work with oscilloscopes a lot, next time you have an oscilloscope together with a function generator, take a close look at what's going on. If you plug your function generator into the oscilloscope, you can see the wave on the screen that the function generator generates. And most of our function generators have a switch on them. You can turn the switch from giving you a sinusoidal wave or a square wave or a triangular wave. take a close look, turn it to the square wave, and take a close look. Expand the scale on the oscilloscope so you can carefully see what's going on here. Of course, the way the function generator makes the square wave is it synthesizes it by adding together appropriately chosen sinusoidal waves. In other words, it does a Fourier analysis. It constructs it by adding up the terms in the Fourier series. And of course, it doesn't use an infinite number of terms. It uses a very large number, but not an infinite number. So take a look, especially right here at the edges. If you turn up the scale on your oscilloscope so you can see this in great detail, you can see these little spikes. Okay?
Do you get the Gibbs phenomenon like on a triangle wave? Or is it just...
No, it's just square waves, I believe. Okay, but anyway, I'm hoping that gives you sort of more of a feeling for how it is that this sum really starts to look more and more like a square wave as you add together more terms in it. And of course, you can do a similar kind of, sketch with other shapes of waves also. But the square wave, I think, is a nice example of this. Anyway, I do want to go back, though, to something that we noted as we did this example. In this example, we noticed that all the b sub n's were 0. Okay, we can actually generalize that in the following way. Notice that our square wave that we started with, as our f of x in this case, okay, here's a graph of it back here. Notice that this function is an even function. Right? F of minus x is equal to f of x. For any negative value of x, like minus pi over here, the function has the same value that it has at plus pi, for example. Right? Or another way of thinking of it, like we said before, if you imagine taking the graph for positive values of x, right, to the right of here, and just kind of folding it over or sort of reflecting it, right, or folding it over to the other side to the negative values of x, it gives you, this graph down there looks like the same thing. Okay? And so if f of x is even, all of the b sub n's are 0. Okay, so the example we just did was a case where that is the case, but it's easy to prove that this is the case. Let's just look at the definition of the b sub n's. Right? We found b sub n by taking 2 over L times the integral of f of x times the sine of 2 pi nx over L dx. And this is especially apparent if we use our choice of x naught of minus L over 2, the usual choice. Then our limits are minus L over 2 and plus L over 2. Well, here's what you need to notice, right? F of x is even. Sine 2 pi nx over L is an odd function. Right? Sine is an odd function. And as you are going to be showing in your homework, an even function times an odd function gives you an odd function. Okay? So an even function times an odd function is an odd function. So the integrand is odd. And I'm hoping you remember from a math class at some point that if you have an odd integrand and symmetric limits of integration, in other words, let's say minus a to plus a, right? Minus L over 2 to plus L over 2. That guarantees for you the integral is 0. Right? So that's why all the b sub n's are 0 for odd functions. And it actually probably kind of makes sense if you think about it. If you're trying to reproduce an even function, you probably want only even functions in your Fourier series, right? And those are the cosine terms. The sine terms are odd functions. They don't have the right kind of behavior, if you added them in, to contribute you know, in this sort of way to trying to construct an even function. Okay, so actually with this example, if we had known this to begin with, we could have said, we wouldn't have even had to work out the integral for the b sub x. We could have just said we know they're all 0 because we know f of x is an even function. So that's kind of a shortcut in doing these problems. Okay? And similarly, if our f of x that we were writing our Fourier series for is an odd function, then all of the a sub n's will be 0. And you can prove that in a similar way. A sub n is 2 over L times the integral from minus L over 2 to plus L over 2 of f of x times the cosine of 2 pi nx over L dx. And if f of x is odd, and we know cosine is an even function, so again, an odd function times an even function gives you an odd function. So again, we have an odd integrand and symmetric limits of integration. And that tells us the integral we have to do here is going to be 0. Right? So that means all the a sub n's are 0. Okay, so if you're doing a Fourier series and you know that your function is either even or odd, you know that, again, if it's even, all the b sub n's are 0. If it's odd, all the a sub n's are 0. You don't have to do the integral. You can just say that at the beginning.
Since we were able to generate a square wave from an even function, does that mean we can generate a sine wave from an odd function? Or
Well,
does it not matter?
I mean, a sine wave is just the first term in the Fourier series, right?
Yeah, so then we want all of our a sub n's to be 0 and that would generate the sine wave for us, correct?
Well, if f of x were simply, you know, sine x, let's say,
Okay.
I mean, that would be a pretty trivial Fourier series.
Yeah.
All the a's would be 0, and all the b's would be 0 except for b1.
Okay.
Right?
Yeah.
And 2 pi would be equal to L, and with n, there's our sine x right there. In other words, that term in the series would be the whole f of x. We wouldn't need any other terms.
Okay.
Right? Okay, I want to just caution you though, right? So you have a shortcut here in cases where your function f of x is either even or odd. But I want to just caution you, remember that not all functions are even or odd functions. There are some functions that are neither even nor odd. Okay? So be careful you don't think that every function falls into one or the other of these categories. It doesn't. So let's do another example. I'm going to leave this general expression here up on the board because that's going to be our starting point. Now, sometimes you will be given a function when you're doing a Fourier series that doesn't look like a periodic function. For example, let's say that we are told f of x is equal to x squared for the interval from minus 1/2 to 1/2. Now, x squared, of course, is not normally considered to be a periodic function, but here's what we mean when you see this in the context of a Fourier series problem. All right, let's look at a graph. So here's 1/2 and here's minus 1/2 on the x-axis. Okay, so over that interval from here to here, if we draw x squared, it looks like that, right? It's a parabola. What we mean when we say this for this interval in the context of a Fourier series problem, what we mean is that instead of continuing the parabola up like this for higher values of x, let's say, we're going to make this function periodic by taking what it looks like for this interval and then repeating it. Okay? So if that's 1, here was 0, that's 1/2, this is 1, this is 3/2, right? And then we'd repeat it again. The next peak would be at 5/2. And same thing down here. Repeat it like this. So this peak would be at -3/2. Right? Now it's, of course, a periodic function. Okay, so we could do a Fourier transform of that. Now the period, what we've done here is we've specified the function over one period. Right? The interval we were originally given is assumed to be one period. So the period is equal to 1 in this example. Right? So L equals 1 in these expressions here. Okay, so in this case, f of x is clearly even. So according to what we've said over there, the b sub n's are equal to 0 for all values of n. Right, so we don't even have to do the integral for the b sub n's, we just know that. So all we have to figure out are the a's. Okay, so these are our general expressions right here. I'll leave those up on the board and work. I'm not going to actually spend the time doing integrals for this one. I'm just going to kind of tell you the results. Okay, so our A naught is given by this right here. L, the period, is equal to 1. So this is 2 times the integral, and f of x is x squared dx. And we're going to go from minus L over 2 to plus L over 2. In other words, minus 1/2 to plus 1/2. You don't have to do this step, but you could simplify it a little bit by doing this. Sort of related to what we said over here. If you had an odd integrand in symmetric limits, you know the integral is 0. If you have an even integrand, and symmetric limits, like minus a to plus a, and if f of x is even, then remember that you can write this as 2 times the integral from 0 to a of f of x dx. Because the negative range of x contributes the same amount to the integral as the positive range of x. So I could write this as 4 times the integral from 0 to 1/2 of x squared dx, because x squared is an even function. Okay? And of course, the integral of x squared is x cubed over 3, so this is 4/3 x cubed, evaluated at the limits of integration. 1/2 cubed is 1/8, right? So we have 4/3 times 1/8. That gives us 1/6. Okay? So that's A naught. And A sub n for n not equal to 0. A sub n is given by this formula, again with L equals 1. This will be 2 times the integral from minus 1/2 to plus 1/2 of x squared, that's f of x, times the cosine of 2 pi nx dx. Right? We just set L equals 1 in the integrand. You can either do this integral by parts. You'd actually have to do it by parts twice, or of course you can look it up in integral tables. Looking up integrals is a perfectly okay thing to do. Right? I'm not going to insist that you do every integral by hand. If you get an integral you look up, that's perfectly fine. If you're doing that on homework or, an exam, you're not going to have integral tables with you. That reminds me of something I have to talk about in a minute, but let me finish this example first. On homework, it's perfectly okay to use integral tables. Just tell me where you looked it up, okay? Whether it's online or in a book or whatever, just tell me where you looked. Anyway, I'm not going to go through the work of doing this integral, but if you do it, you will find that a sub n is equal to 1 over n pi quantity squared times the cosine of n pi. And we can usually, we'll often get a sub n's and b sub n's that involve sines and cosines like this, and when you do, you should simplify them. Remember here that n is an integer, right? And so think about the cosine of an integer multiple of pi, and I usually find it to be helpful to draw a little sketch at this point, right? So cosine looks like this. This is 2 pi, this is pi, this minimum here would be a 3 pi, the next maximum would be a 4 pi, and so on. So it looks like for even values of n, the cosine of n pi is plus 1, right? Like a 2 pi and 4 pi, for example. So this a sub n will be equal to 1 over n pi squared for even values of n. And for odd values of n, like pi or 3 pi or 5 pi, the cosine function is minus 1, making a sub n minus 1 over n pi squared for odd values of n. Okay. So that means our f of x right, so, and our final answer for any of these Fourier series problems should always be to just write out the whole Fourier series, well, not the whole thing because it's an infinite series, but write out the Fourier series, okay? So go back and plug your a sub n's and b sub n's back into this general expression right here, okay? So for our case, L is 1. So let's see, we've got a naught over 2. A naught was 1/6, so a naught over 2 is 1/12. The next term will be for n equals 1. That's an odd value of n, so this is the formula for the a sub n. So it's minus 1 over pi squared for n equals 1. And remember, L equals 1 here, so it's a cosine of 2 pi nx, so with n equal 1, it's just a cosine of 2 pi x. The n equals 2 term, we have a positive 1 over n pi squared, n is 2, so that's 1 over 4 pi squared. That multiplies the cosine of 2 pi nx with n equals 2, in other words, the cosine of 4 pi x. The next term will be a minus 1 over 9 pi squared. Right, using this with n equals 3 times the cosine of 6 pi x plus 1 over 16 pi squared times the cosine of 8 pi x, and so on. Okay, well, there's another way of writing Fourier series. I'm sorry, I just reminded myself I wanted to talk to you about one other thing. And I should have done this at the beginning and I forgot about it. But an integral that was difficult to do is what reminded me of this. I have an apology that I owe to you, because on the exam, remember I told you that if you were getting an integral that you couldn't do, that you were making mistakes somewhere? Well, I screwed up. On problem 2 on the exam, part B was no problem. Should have been able to do part B perfectly okay. But in part A of problem 2, you did end up with an integral that was kind of hard to do. Okay? It ended up being an integral. You should have switched to polar coordinates at some point, and you would have gotten an integral of cosine squared theta, sine squared theta, d theta. I think the limits were 0 to 2 pi of theta, if I remember correctly. And that's an integral that you probably don't know how to do off the top of your head. And I apologize for this. The reason I screwed up, it gets back to the question I think Andrew asked earlier about take-home exams. Remember I told you why I don't do take-home exams anymore, because the solutions are available to any problem I can think of and people just copy them. Last time I assigned this problem, because I do sometimes reuse problems over the years, and the last time I used this problem was back when I was giving take-home exams, and it's no problem on a take-home exam if you get an integral like this, because you can look it up, right? But on an in-class exam, of course, you're not going to have integral tables available to you, and I had just forgotten that this problem involved an integral that had to be looked up. So I apologize to you. It was my mistake. I should have checked that out ahead of time, and I didn't. So what I did in grading problem 2A is if you got to this point, I gave you full credit. Okay, I didn't expect you to evaluate this integral. If you did evaluate it, you would get the same answer, of course, as part 2B, because part 2A and part 2B were two different ways of working the same problem, which should give you the answer. Okay, so again, I apologize for that one. Okay, so anyway, we've written Fourier series in terms of sines and cosines, right? But we know that sines and cosines can be written in terms of complex exponentials also. So it should be possible to write a Fourier series in terms of complex exponentials rather than sines and cosines. So let's look at that way of doing it. Sometimes that's more convenient, okay? So in terms of complex exponentials,
Professor?
uh-huh.
Would this be a good time for a break, or are we not doing a break?
Oh, yeah, I'm sorry, I forgot. Yeah, let's do a break now. Okay, so anyway, we said we were going to write a Fourier series in terms of complex exponentials.
Too tired to be excited.
So your book, just like your book did for the sine-cosine Fourier series, which was, the ones in terms of sines and cosines, in other words, this right here. Remember we said your book did, first of all, the case where our function f of x has a period equal to 2 pi. And if L equals 2 pi, then of course the L's and the 2 pi's cancel in all these terms here. And then they go through and they rederive everything again for an arbitrary period. Well, they do exactly the same thing for the complex exponential Fourier series. So again, they go through it twice. Once for a special case of a period of 2 pi, the second time for the case of an arbitrary period. Just like we did for the sine-cosine Fourier series, I'm going to do the arbitrary one just to begin with. Okay? You can always then look at the special case where L equals 2 pi separately. So our general expression for a Fourier series in terms of complex exponentials involves coefficients. We'll call them C's. C sub n's instead of A sub n's and B sub n's, like we did for the sine-cosine Fourier series. So C naught is our constant term. C1 gets multiplied by a complex exponential e to the 2 pi x over L. Then there's a C minus 1 term, which gets multiplied by e to the minus 2 pi I x over L. And then a C2 term that gets multiplied by e to the 4 pi I x over L. And a C sub minus 2 term that gets multiplied by e to the minus 4 pi I x over L. And so on. Or in other words, if we write this in summation notation, this is a summation from n equals minus infinity to infinity. N is an integer, but it can be either positive or negative, right? And we have C sub n times e to the 2 pi I nx over L. Okay? So the positive values of n give you like the C1 and the C2 terms. The negative values, since n can be a negative number, also give you these terms right here. And obviously, in a sum like this, you can't start and write the first term as n equals minus infinity, right? So the way we usually write a sum like this is we start at n equals 0. That gives us the C naught term, right? Because of course, when n equals 0, you have an e to the 0, which is 1, so it just gives you C naught for that term. And then do n equals 1, then n equals minus 1, then 2, then minus 2, then 3, then minus 3, then 4, then minus 4. In other words, count in both directions from n equals 0, right? That's the easiest way to write. Now, you may not have anticipated that there were these negative terms in here as well, but they have to be there if you think about it, because remember in this expression with the sines and the cosines, remember that the sine of x is equal to e to the ix minus e to the minus ix over 2I, and the cosine of x is equal to e to the ix plus e to the minus ix over 2. Right? So if you were to just replace these sines and cosine terms by complex exponentials, you would get exponents that are positive and exponents that are negative. Right? So that tells you there are going to be these negative terms like this one and this one as well. Okay, so this is the general expression for a Fourier series in terms of complex exponentials. And the question, of course, the same question we had for the sine-cosine series is how do we find these C sub n's, right, these coefficients? Well, if you remember how we did it for the sine-cosine series, the procedure we went through to derive the expressions, these expressions right here for the a sub n's and b sub n's, we use the concept of the average value of a function, right? And we're going to do a similar thing here. So just kind of as an aside to help us answer this question, let's look at the average value of the function e to the 2 pi I n x over l. Right? The form of the exponential we have right here. So e to the 2 pi I n x over l, average value of that, remember a line over it like this means an average value. Let's first of all look at the case where n is not 0, okay? The n equals 0 case we'll have to treat separately.
Professor, what does that say right there? Aside?
Yeah.
Oh, okay, that's fine.
Okay, so remember the concept of an average value. The way we find it is we do 1 over L, the interval we're looking at. L was, remember, the period of our function. We're going to take an integral. We'll put the limits as minus L over 2 to L over 2. Again, that's what we usually use as the limits here. Right? We said that was the usual value x naught we used here. So let's stick with that same value here. The function is average value we want gets put in the integrand here. So e to the 2 pi I n x over L dx. Well, we know how to integrate an exponential. In fact, you know, that's one of the main advantages of remembering these expressions for sine and cosine. I mean, like I told you earlier, you can use these to derive any trig identity you want. But the other big advantage that these expressions have is if you're doing, let's say, an integral that has sines and cosines in the integrands. If it's a complicated integral, you may not know what it is, right? You may have to look it up if it has sines and cosines in it, like the one on problem 2A on the exam, right? But if you replace the sines and cosines by these expressions in terms of complex exponentials, you know how to integrate an exponential, right? That's easy. And a complex exponential works the same way as a real exponential. So that makes integrals involving sines and cosines a lot easier to do too. In fact, problem 2 on the exam, if you had already known this when you were working that problem, you easily could have done that integral that way. So anyway, the integral of an exponential, right? Well, first we've got the 1 over L out front. The integral of an exponential gives us, of course, the same exponential back again. So e to the 2 pi I n x over L. And then we have to divide by the coefficient of x in the integrand here. So in other words, that's going to put a 2 pi I n in the denominator and an L in the numerator. And of course, then the L's will cancel. And we have to evaluate this at the limits of integration, L over 2 and minus L over 2. Okay, so we've got 1 over 2 pi I n out in front. And when we plug in x equals L over 2, the upper limit, the L's and the 2's will both cancel. We'll have e to the I n pi. And then subtracting at the lower limit, we have the same thing except a negative sign in the exponent is e to the minus I n pi. Well, let's use this. This looks a lot like a sign, right? We have one e to the plus something minus e to the minus something. We've even got the 2i, 1 over 2i out in front. So in other words, this is the sine of n pi. Right? That would be e to the I n pi minus e to the minus I n pi over 2i. That leaves a 1 over n pi out in front. So sine of n pi over n pi. Well, remember that n is an integer. And the sine of an integer multiple of pi is 0. Okay, so the average value of this function is 0. Now that was for non-zero values of n. Let's do the case where n equals 0 separately. Okay? If n equals 0, we have e to the 0, and e to the 0 is just 1. If we take the average value of a constant, we get that same constant back again. Right? So that one is 1. But for any non-zero value of n, the average value of this function is 0. So let's use this then to find our coefficients, the c sub n's. So let's first of all talk about how we find C naught. Okay, so to find C naught, let's take the average value of our basic Fourier series equation, this equation right here. Right? In other words, f of x is equal to this sum of c sub n times e to the 2 pi I n x over L. Okay, so on the right-hand side, when we take the average value, c sub n is some constant. It can be pulled out of the average value. Right? So the average value appears only over the exponential. Or if you prefer, right, writing out the definition of what you mean by the average value here, the average value of f of x is again 1 over L times the integral of f of x dx from minus L over 2 to plus L over 2, right, over one period. That's the same thing as what we mean by the left-hand side here. And on the right-hand side, if you prefer, you could write this as a summation of C sub n over L, right? For the average value there, you could replace the same integral I wrote for the average value right here. Well, there's a sum here, remember, from n equals minus infinity to plus infinity, and n is an integer. Okay, so there are all sorts of different terms in this sum here, and most of them are 0. Okay, because we found that this average value, or equivalently this integral right here, is 0 for all values of n that are non-zero. Okay? For n equals 0, the average value isn't 0, but for all other values of n, it is. So when we do the sum over n, this integral here, or equivalently this mean value right here, is 0 for all values of n except n equals 0. So the only non-zero term in this sum is for n equals 0. And in that case, you just get a C naught over L, because this integral right here, well, let's write it out, okay? This integral for the case where n equals 0, we have an e to the 0, so there's just a dx in the integrand. So the integral of dx is x. We evaluated the limits of integration. We get L over 2 minus a minus L over 2, or in other words, plus L over 2. That cancels with the L in the numerator, or in the denominator rather. So this is just C naught. So in other words, C naught is equal to 1 over L times the integral of f of x dx. Right? The left-hand side right here. And we had limits from minus L over 2 to plus L over 2, but just like with the sine-cosine series, we can actually use limits from x naught to x naught plus L for any value of x naught we want. Again, usually we choose x naught to be minus L over 2, or probably the second most common choice is x naught equals 0, but really you could use any value of x naught. Okay, so that's how we find the C naught. Let's similarly talk about how to find then the C sub n's for non-zero values of n. Okay, so let's multiply our Fourier series basic equation. In other words, this equation right here. Let's multiply both sides by e to the minus 2 pi I mx over L. For some value of m. In fact, in the notation I'm using here, we're going to end up finding C sub m. Okay, so let me change n to m. Although obviously, when we get our final answer for C sub m, you could switch from m back to n again if you like. Okay, so for some value of m, we're going to multiply that whole equation through by e to the minus 2 pi mx over L, and then take the average value. Okay, so on the left-hand side, we we've got f of x, we're multiplying through by e to the minus 2 pi I mx over L. On the right-hand side, we've got a sum from n equals minus infinity to plus infinity. Remember, n is an integer. And in the sum, we have a c sub n times e to the 2 pi I nx over L is what we had originally. But remember, we're multiplying both sides through by e to the minus 2 pi mx over L. And when we have two exponentials multiplied together, we can just add the exponents. Right? So we're going to add that exponent to this exponent. Well, notice both exponents have a 2 pi I x over L in them. The only difference is that one has an n and this one has a minus m. So when we add the exponents, we're going to get an n minus m. Okay? 2 pi I times the quantity n minus m times x over L. Okay? And then we're going to take the average value. So we'll put bar over that on that side, and on this side, the c sub n, since the constant, can be moved on in front of the average value. Okay? Or in other words, if we write this in terms of integrals, rather than just the bars denoting the average values, on the left-hand side, this average value is the same as 1 over L times the integral of f of x times e to the minus 2 pi I mx over L dx. Right? We're going to use limits from minus L over 2 to plus L over 2. And on the right-hand side, we've got a summation from n equals minus infinity to infinity, c sub n. And this average value, we're again going to put 1 over L times the integral of the thing whose average value we're taking, so 2 pi I n minus m x over L dx. And we're going to integrate again from minus L over 2 to plus L over 2. Okay, well, all of the terms in this sum, right? We've got an integral for each term in the sum. And what we said over here, right? We said that this mean value, or equivalently this integral here, was equal to 0 if n was non-zero. Well, this integral, if we compare it to the integral we have now, the n over there is replaced by n minus m. So in other words, the integral here is equal to 0 except if n minus m is 0. Right? Or in other words, if n equals m. That's the only non-zero term in this sum. Okay? So we got an infinite sum or all these possible values of n. All of them are 0 except when n equals m, right? There'll be one term in that sum when n equals m. M is some integer, I guess I should have said here. It's an integer. Okay. And so that one, right? The only non-zero term then will be c sub m over L, right? When n is equal to m. And in that case, all we have left in that integral, when n equals m, the n minus m here will be 0. We'll have e to the 0, which is 1, so just dx. This is the same integral we did over there. Right? This is just L over 2 minus a minus L over 2. In other words, L in square brackets there, that cancels the L down there, so this is just C sub m. Okay, so C sub m is equal to the left-hand side of what we have here. So in other words, just to summarize here, C sub m is equal to 1 over L times the integral, and again, we can do limits of x naught to x naught plus L, although we again usually use x naught equals minus L over 2. And in the integral, we've got an f of x times e to the minus 2 pi I mx over L dx. actually, we can see this will work even though we said this is going to be for m other, any other value other than 0. It actually works for m equals 0 too, because if we use m equals 0 in here, if e to the 0, which is 1, so the only thing in the integrand is an f of x. In other words, it agrees with this expression down here. Okay? So this actually works for all values of m, including m equals 0. Okay, so that's how we find our expressions. And again, you could change from m back to n if you prefer in this expression. Okay? And so that works for all values of m, 0, positive, negative, right? Any of them. Okay, so there is our general expression then, including how to find the coefficients for the complex exponential Fourier series. So let's do the same example we did earlier, the one that we started last time and finished up at the beginning of class today, that square wave example. So, again, remember that our function looked like this. Right, the top here was at 1, the bottom was at minus 1. This was pi, this was minus pi, pi over 2, 3 pi over 2, and so on. So in other words, our f of x, if we define one period from minus pi to pi, our f of x was plus 1. For values of x between minus pi over 2 and plus pi over 2. And our function value is minus 1 for values of x between minus pi and minus pi over 2, and between pi over 2 and pi. Oh, we're not going to have time to finish this. Yeah, I'm sorry, I didn't notice what time it was getting to be already. Okay, I guess we'll stop before we work through this example, but we'll do this next time then. We'll use this expression right here to find the c sub m's for this example, and we'll actually, once we get that final result for our Fourier series written out, we'll be able to see that it's the same result that we got in terms of sines and cosines. Okay?